For the people who do not know, I am right now here in US, southern part of US. This is Austin, and we zoologists always think about animals and stuff. So this is the information that I'm sharing. So Austin is actually the home for Mexican free-tailed bats, which migrate during the winter season from the center or northern region of US towards the Mexico. And but for 4 or 5 months during the year, they reside at various pockets in between. So one such place is Austin, where about 10 to 15 lakhs of bats actually reside just under one bridge, and you can visit them every year. So that's just one information that I just wanted to share with the students of zoology. So now I'm going to go into the topic, and before I start discussing about that Lotka-Volterra equation, what I'd like to point out is that what you may learn in this lecture. I'm talking about the students who are to study this topic. I always think this before I start understanding or trying to understand the concept, that why should I study this, how is it going to help me. So we'll go into that. Also, the basic concept of the model or the equations, or how that equation can be used to interpret different aspects of biology. And then third, that would be one of my primary goals, is that to introduce you to the world of mathematical modeling. When I was a student, especially from places like Bardhaman, this was not very well introduced to the students. Students avoided it for some reason, and I felt a when I grew up as a student, I felt a disconnect when I started doing experiments, finding out that there is a big vast world of mathematical modeling and uses of mathematical modeling that we do not appreciate, we do not understand, do not learn. So in today's lecture, I will try to see whether I can motivate you to pick up this subject and read yourself. What I'm not going to do today, what is not the purpose of this lecture, is let you feel or let you know how to write in exams. That's not the focus of this lecture. You'll not be able to find out anything new. You already have books and notes that will help you. My focus would be to make you understand different concepts associated with it. This is also not the purpose of this lecture, that is how to easily memorize the mathematical section. And third is that it is not the purpose of this lecture is to not let you ask me questions. So this is an open forum. I want you to ask me questions anytime you want. Just stop, unmute yourself and ask me the question. And I'll not feel interrupted. It will be great if you have any questions, I'd be happy to answer them. Also, the thing is, if you have a problem with the language, I have a problem with the language. What I want from you is you just ask. Bangla question karo, not a problem. Let's have a discussion. All right. So in today's talk, I'm going to talk about 5 different things, connected 5 different things. First, I'm going to talk about mathematical modeling and and very basic concepts of it, so that we can understand what the Lotka-Volterra model is all about. Then I'm going to talk about ecological concepts of growth and competition in very brief, so that we can actually go to the main topic, that is Lotka-Volterra. And then we're going to see how Lotka-Volterra models can be used in different aspects of biology, and you'll be stunned to find out the extreme examples of the application that people have done using Lotka-Volterra models. And finally, we'll conclude and get some take-home messages from this lecture. All right. So first, mathematical modeling. So for this, what I'm going to do is I'm going to start with an introduction, what is a mathematical model, and how to build one. This is the so whenever I was trying to prepare for this lecture, this came to my mind. Whenever I take classes here for mathematical model, or like, and I ask this question to the students, and this is called a Fermi question. A famous scientist, Enrico Fermi, popularized this mode of questioning or modeling. And I made this question to be specific to Bardhaman. And let's see whether you can like try to answer this. Is it possible for you to guess how many TV repair mechanics are there in Bardhaman town right now? I'm going to just give you one information, that is, give or take, the population of Bardhaman is about 4 lakhs or 400,000. Is it possible for you to know? If you think you know the answer, you can do it. Just chat, write in the chat. Is it possible? Yes or no? Is it a weird question? Well, let's see. So let's start off with some assumptions. Yes. No. So the population is 400,000 or 4 lakhs. If there are on average 4 people per family, then there are 100,000 families in Bardhaman. And if each family wants one TV, on average, there can be many families which do not have TV. There can be many families which have more than one TV. And so on average, if each family wants one TV, then the total TV would be about 100,000. And each TV needs repaired. This is also our assumption, once in every 4 years. So every year, the number of TV repaired would be 25,000. And if a mechanic who is there, who is going to repair it, repairs 2 TVs a day, because he's also an electrical mechanic, so he has other things to do, so he can only perform 2 TV repairs a day. He does that 5 days a week, 50 weeks a year. Then the total TV repaired by that mechanic is about 500. So we can actually estimate that number of TV repair mechanics would be about 50. And if we are like 4 to 5 times within the range of error, like if let's say there are 250 mechanics in Bardhaman, then we are close. We did a very good job. And this is one example of mathematical modeling. We had some estimate starting from some very simple assumptions. The original question that was asked by Enrico Fermi was, how many piano tuners are there in Chicago? So the people who can fix the piano and tune the piano. And Enrico Fermi asked, can we just sit on a sofa and calculate out, just by thinking, how many piano tuners there are possible? I just changed that question to suit the audience here. So that was an example of mathematical modeling. What mathematical modeling is that you take information from real world. So there are some observations, then you conceptualize it. You have a framework. Like we had some information from the real world, like there are 400,000 people in Bardhaman. Then you conceptualize it. That is, you have some observations like, okay, there may be on average 4 people per family. Then you have a model. Then you predict, and then you go back and check whether that is true or not. And that's the way the science of mathematical modeling works. So mathematical model is a representation of a system with a set of equations that correspond to hypothesized relationships among systems components. And it's different from natural experiment, because in natural experiment it is an approach to hypothesis testing. That means you have an hypothesis here. There is a prediction in the conceptual world that relies on the phenomena that you have initially observed. Now, whether your concepts are correct or not, that would be tested by experiments. So there are 3 components to mathematical modeling. And that is important for even Lotka-Volterra model. We'll see. First is postulates. Then there are distributions, and there are coefficients. So in the previous example we just saw about TV repair mechanic, the postulate that we had was each family wants one TV. That was our postulate. It has to be there, otherwise our estimate would be very off. Then we had a distribution. So distribution here means the probability. So what is the probability of a number of individuals in a family? We assumed that it is 4. So the number of number of families that we calculated was calculated from a probability distribution. We'll discuss that in little detail later. And then we had a coefficient, and that is total TV repaired per year. So using postulates and distributions and some assumptions, we could go to we could hypothesize something, and we made a coefficient, and then we calculated out something. So these are the 3 different components of mathematical modeling. So postulates are basically logic, and if your logic fails, then you go back and form a new postulate until you make it right. So that way, mathematical modeling and experiments can go hand in hand by correcting and incorporating improvements in the model every time a new iteration is made. Distribution, on the other hand, are just calculations of probabilities. So that means you have many different kinds of distributions. And why I'm talking about this, because we'll take some information from here and we're going to apply this to the Lotka-Volterra model. So there are many kinds of distributions. We'll just talk about few. So there are probabilities like uniform distributions, like a deck of cards. When every card has equal probability of drawing out by you, so you just blindly pick a card, and you can have 1 by 52 possibility of drawing that card. And that would be same for every card, so that is uniform. And this kind of probability can be applied to various different things. I just pointed out one, like lottery or in casinos. Then there can be distributions, like discrete distributions called as Bernoulli distributions, where there are only 2 events, like tossing a coin. So there can be either heads or tails. And these kinds of binary or discrete, there are only 2 events that are happening. So you're calculating what are the chances of happening either head or the tail. That percentage can be calculated, and this kind of distribution can be used in computations, writing different algorithms, and many other processes such as electrical circuits and stuff. Also, we have very popular normal or Gaussian distribution, where the population will have the majority of the population will fall into this area. So this is the graph that shows the Gaussian distribution. Examples would be the height of humans, also how antibiotics kill bacteria. So there are very different ways. I just made a simple statement here, but that's a very complicated thing that is used to understand how antibiotics and bacteria can like have a ecological competition. Then there are Poisson distributions. So Poisson distribution is nothing but frequency or probability of finding out discrete events that is happening in one instance. Like how many leaves there are one branch of a tree. That is a Poisson distribution, and that can be calculated out. And using Poisson distributions, weather forecasts are made. So there are real life, so these are examples that you can follow on the left, and these are real life examples of usage of these distributions. One such probability distribution or equations are called as Kolmogorov equations. This seminar, we don't have enough time to go into that, but this is the basis of Lotka-Volterra model, who independently use the basis of Kolmogorov equations and utilize that to make their assumptions and mathematical models. So Lotka-Volterra just wanted to use a specific type of probability distribution to predict the future, predict the outcome later. And then there are, as I said, there are three components. The third component is coefficients, which is nothing but the rules or theories that you make out of your assumptions and after finding out or calculating out your probabilities. So going to the second part, that is growth and competition. So this is a lecture on itself. I'm just going to briefly touch upon this so that we can actually go to Lotka-Volterra model. And this is the only information we need to know to understand Lotka-Volterra model. So N is the size of a population. That means, let's say there are 10 deers in Ramana Bagan in Bardhaman. So that's the N, a capital N, or the size of the deer population in Ramana Bagan in Bardhaman is 10. And let's say every year one new deer is born. So the growth rate would be the change that is happening every year divided by the total size of the population. So that, let's say if there is one deer that is being born every year, and there are total 10 deers in the Ramana Bagan, then the growth rate would be 1 divided by 10, that is 0.1, 0.1. So change in population is always calculated, and if you have taken courses in calculus, you will know that you can write a change, small changes in anything using differential component of an equation. So dn by dt, that is the change in n over time, can be written as a product or multiplication of r, that is the growth rate, and n, that is the size of the population. So in case of the deer population in Ramana Bagan, the r was 0.1 and the n was 10. So that means the change in population would be 0.1 multiplied by 10. That would be equal to 1. So that would, and that's it. So every year it's going to increase 1 in its population. Generally, n and r, if the environment does not change and there is no specific like drastic events happening, due to evolution, the r remains relatively constant and the population itself tries to achieve an equilibrium where the n is very stable. But in theory, if a population is growing constantly, continuously, if there are no limits, there is no limits of resources, and there is no selection pressure that is happening, then what you get is an exponential growth, where the population size will increase over time exponentially, and you will get a J-shaped curve. You can see this is J-shaped. But this is theoretical and not, I mean, it's possible, and we do see examples of that, but it is followed by some other events. Because if this was true for one organism, that organism would have just grown and would never cease to exist. What happens is that there is a concept called as carrying capacity. That means in every situation, depending on the environment, there is a limit to the number of organisms of a species that can exist there. That is the maximum number of n max. That is also called as K, or carrying capacity. And now you can change this equation by introducing a carrying capacity coefficient. And this is called as the model of logistic growth. Why? Because you are actually using logistics or some You're taking into consideration what is happening in the environment to fit or to calculate out your model. And you can see the same equation as seen on the left is there on the right as well. It's just that there is a coefficient of k that has been applied. So take what is this coefficient? Why did we apply this? So just think of an example when k is far greater than n. That means n is very close to 0. Then the n will become 0. So k by k will become 1. So this equation would be same as this equation. So there is no change. So that means when the population is just at the initial phase, then there is no limit to its growth. It's going to grow. But as the growth increases, the n will increase. So this value of 1 will decrease and go towards some value. Not 0. It will not become 0. May become 0, but generally it doesn't become 0. So what will happen? The number of organisms that was increasing over time will decrease because the carrying capacity is being approached. So that's why what you'll find is a sigmoidal curve or S-shaped curve, where you'll find that after a while the population is reaching a limit. So let's take some example and of what kind of approaches organisms take for their growth in the nature. And actually organisms take both of these uh, approaches, and we'll see the examples. So the organisms which take the the J-shaped curve is called as the R-selected population, because they have been selected to grow like that. The natural selection has fine-tuned their growth and death cycle in such a way that they grow like that. And you can have many examples. This is the theoretical model, but that's not true. After a while, as I said before, this is theoretical. After a while, it's going to reach a, a phase where it cannot grow exponentially anymore. And what can happen is it can go through cycles of phases like this. So it grew, then it died off, then it grew, then it died off, then it grew and died off. These are called as growth and bust cycles. And one example would be the growth of lemmings that are found in Arctic, where they grow and die with seasonal changes. Or there can be examples of exponential growth followed by a little bit of death and some fluctuations in when it's reaching the carrying capacity. And the example would be meerkat in the African savannas. Whereas the majority of the organisms follow this K-selected growth, where there is a lag phase followed by a log phase followed by a plateau, because it is reaching the carrying capacity. The environment cannot sustain more individuals than it's there. And there can be variations to that, like this. There are many plants which grow like that, or it can look like almost like a straight line. It looks like a straight line, but it's not, because there are like it's a big, very slopy, long S-shaped curve. And we're just looking at a small section of it, and that's why it looks like that. One example would be human growth. So various growth strategies are applied by organisms for survival in natural environment. But if it was the only interaction of the organism and the environment, then we could have predicted their growth easily. That's our goal. We want to predict how well an organism grows. But the situation is not simple at all, because there are multiple species who are competing against each other, and also the environment is always fluctuating or changing. So that means we have to incorporate those things into our model or mathematical model also, if you want to predict what happens to an organism. For example, we can we can fairly predict what will be the number of lemmings in a certain time of the year because we already know how it grows. So we have a mathematical model and we can predict the growth of lemmings in an Arctic circles. But not all we will not be able to predict all organisms' growth using just simple models like this, because as I said, there is a change in environment, but also there is competition. There are two types of competition that is happening in nature. One is intra-specific competition. Lemmings are fighting with other lemmings. Uh, that is part of the growth dependence that we saw before. So the carrying capacity is part of it. What we are interested for this lecture is interspecific competition, where competition is among individuals of a different species. So two different species or multiple different species are fighting against each other or competing against each other for survival. And there can be many different outcomes. The question then becomes, can we use mathematical models to predict who is going to do what, how well a species is going to do or perform in a specific scenario? So let's say this is species 1 and let's say this is species 2, and there can be intra-specific competitions, or there can be inter-specific competitions. Species 1 and species 2 are interacting with each other, but it may be either symmetric or asymmetric. That means both are equal, they're fighting off each other very nicely, they can fight each other very nicely, or, which is more common, one is winning against the other. So what is happening is this is fighting and winning against this one. So there can be asymmetric competition, and that way one species will outcompete other species. But this is very qualitative or generic way of saying who is going to win, who is going to lose, who is going to survive. Can we actually use mathematical models to predict this? Well, there are some more things to consider before we go there, and that is there can be, what kind of interactions are we talking about? So there can be interference competition. Like, I've just used a random example. Let's say there is a patch of grass that can be eaten by a cow or a horse. And let's say the cow and horse are actually physically fighting against each other and not allowing each other to eat the grass. In that specific scenario will be interference competition, because the cow is actively interfering, or actively interfering the horse, or vice versa, from eating the grass. The second example is exploitative competition, where the cow has eaten all the grass, so the horse can't eat anything. So they are using the same resource, and because the resource has been utilized, there is nothing left for it. So although they were not actively competing for it, there was competition. And third is apparent competition. So the cow and the horse are on two sides of the grass. They're trying to feed the grass. It may appear to you they're in competition, but maybe there is a controller like a human who is the cattle grazer and who is controlling how they behave, and so it may be there is a competition, but actually it's not. There are fine-tuning factors which will control it, and there is basically less amount of competition. So there are different possibilities that exist when organisms interact with different species interact with each other. So let's go into the Lotka-Volterra model. So this is the background that we have. We know little bit of about what mathematical modeling is, what you can expect from mathematical model, and what a basic idea about growth and competition in ecology. And let's go into Lotka-Volterra. So this is Alfred Lotka and Volterra. And if you want to read a nice book about how they came about their modeling, the history about it, you can read this book, Modeling Nature. They calculated this separately. Lotka was a insurance company calculation expert in New York, and Vito Volterra was a professor of statistics in Italy. So, as I said, In a model, there are in mathematical model, there are three different things. So let's look at this example. There is a snake species and there is a rat species. And Lotka and Volterra had these three things in their model. The for postulate one was that species one will affect the number of population of species 2. So there is a competition, the predator prey model. So the number of rats will be affected by how many number of snakes are there. Second is the distribution. Remember, we discussed about Kolmogorov equations, where we discussed how probabilities can be calculated. So there are a set of equations called as Kolmogorov equations. Those kinds of equations were utilized by Lotka and Volterra to come to their model. And they generated this coefficient called as coefficient of competition. So this is the basic model for species 1 growth that we have already discussed. The change in population, that is dn1, because this is for species 1, over time is r1, the growth rate of species 1, and n1, that is the population size, multiplied by k1 minus n1 over k1, where k1 is the carrying capacity of species 1. I would have loved to use board and give this lecture to you in person, because this needs writing on the board. Unfortunately, we are living in a world where we have to do it like this. So what Lotka and Volterra did is that they introduced this factor, coefficient of competition, where they said that the number of individuals and how they are competing against each other will also impact how the change in the number of individuals is happening over time within a population. So not only the carrying capacity will control the growth of that population, but also the competition and the number of individuals of the species 2 will control how many species 1 individuals are there. So that is, this alpha is called as the coefficient of competition. Same way you can calculate for species 2, and here, for example, we're calling it as beta, and this species has its own population size, that is n2, own growth rate, that is r2, and own carrying capacity, that is k2, which are all different from species 1. So this is our equation, and Lotka-Volterra argued that let's see what happens in an equilibrium. That means when there is no change in the number of species. So all of them are like equal at the same time. What will happen? Can we calculate out from something from there? So when dn by dt becomes 0, that means the entire thing becomes 0, which means there are three possibilities. R1 is 0, N1 is 0, or this part of the equation is 0. Then only this can be 0. But in Lotka-Volterra model, R1 cannot be 0 and N1 cannot be 0. So that means this component of the equation must be 0. So from there, you can simplify. So K1 goes here, and so it becomes K1 minus N1 minus alpha N2. Finally, you get K1 minus alpha N2, and that equals N1. So you can rewrite this equation in this way. N1, that is the number of population in species 1, is equal to K1, that is the carrying capacity, minus alpha N2. And alpha N2 is the contributing factor from species 2. This equation should look similar to you, because it is similar. It is almost like y equals to mx plus c, where this part is the y, this part is the mx, although this is negative, this is not positive. So it's y equals to negative component of mx plus, and this is the c. So if we now plot n1 and n2, that is y and x, we will expect a straight line. And the straight line will have a slope, and the slope will be m or alpha. Let's look. So if we plot the number of individuals that are present in a population of species 1 on x-axis, and number of individuals that are present in a population of species 2 on y-axis, n1 and n2, assuming that there is no change in either of the numbers, that is dn by dt is 0. So for example, let's look at for n1, when dn1 by dt is 0, we can use this y equals to mx plus c type of equation to get a straight line. Because this is negative, it will become a slope. Not only that, you see that this line intersects where n2, that is the value of y, is 0. All the values of y on x-axis is 0. So here n2 is 0. That means here n1 becomes k1, and that means this is k1. Similarly, on this side, n1 is 0 because all the values of x on y-axis are 0. So this is where n1 component of the equation is 0. So this becomes alpha n2 equals to k1. So that means n2 equals to k1 by alpha. So this is k1 by alpha. So these are the two components of a Lotka-Volterra plot. We have to remember this so that you can apply this in the later models. Now, the second part of this is you can apply the same thing for species 2. That is so you'll get k2 on the y-axis and k2 by beta on x-axis. So now, if you want to see what happens to both the species who are like coexisting together, you will get what we call as IsoClients, where there are two lines which have similar types of slopes. They are not meeting each other. And there are four possibilities that exist with it. There are various different kinds of possibilities, but we are going to talk about mainly four. So what does this plot means, and what can we infer from this kind of analysis? So what Lotka-Volterra assumed is that along this line, if you take any value of n1 and n2, that is number of species, number of individuals of species, the values, the species will be at equilibrium. Both the species will be at equilibrium. Their total number will not change. So this line represents where no species will either win or lose. There is unchanging. But if there is a situation of where the number of individuals is this, or number of individuals for species 1 is this, and number of individuals for species 2 is this, which is below this line, that is this dot, then species 1 will win. And this is symbolized as this arrow indicating growth in x-axis. If there is a growth in y-axis, then it will be symbolized in other way. So that will happen if the number of individuals are here. So I'll just repeat. So if the number of individuals are below this IsoClient line, then it is the number of individuals are going to increase over time. And if the number of individuals are above this line, then the number of individuals are going to increase. So below the IsoClient means increase, above the IsoClient is decrease. So similarly, we can use for species 2, and you can have 4 different scenarios. For in the first situation, so I'm repeating this, I didn't know that I got disconnected. Let me see. My screen is visible, right?
Yes, please go ahead.
Okay. So let's look at this situation where this red dot means that this is the number of individuals in species 1 and species 2, and this is below both of these lines. So that means species 1 and 2 both are going to survive and will try to reach towards equilibrium here. But if it is above these two lines, then both of the species are going to lose out and they're going to come to this equilibrium. And these arrows indicate that. But in this intermediate zone, which is above yellow line but below blue line, species 1, which is the blue line, is going to win because it is below the blue line. You remember, if you remember, we discussed this. This below isocline is increase, above isocline is decrease. So you can see that here. Below isocline there is increase and above isocline is decrease. In this situation, it is below isocline 1, that is the blue one, above isocline 2, that is the yellow one, and that's why the blue one is going to win. So species 1 is going to win. So then there is a second scenario where the blue line is on the top and the reverse is going to happen. So so in this scenario, both the species are going to win. In this scenario, both the species are going to lose and will try to come to this equilibrium. And intermediate, this is below yellow and above blue line. So that means because it is below yellow, the yellow one is going to win. So this is situation 2. If situation 1 and 2 both had parallel lines, but not necessarily there should be parallel lines all the time, unless they intersect across each other, the same set of principles can be applied. But let's look at a situation where the lines cross, that is situation 3. And so there are 4 segments now. 1, 2, 3, 4. In this first segment,
Souvik, I'm sorry to interrupt you. Are you changing the slide?
yes, I am.
I think it's not reflected in the screen. Can you please reshare the power presentation?
Yes, I'm so sorry. I don't know what is happening. Is it visible now? The screen?
Yes, it is.
And is it changing?
Yes.
Okay. My God. All right. So this is situation 1 where the species 1 wins because the blue line is above the yellow line, and this is situation 2 where the second species wins because the yellow line is above blue line, because in most of the situations, so in the first 2 instances, both will either win or both will either lose, but in the intermediate zone, the yellow will win. So these 2 instances, species 1 and 2 will win. In this, but on these first 2 examples where we saw that 2 lines are not intersecting with each other, right? So that means these lines, until they intersect, the same set of principles can be applied. Now, what happens when it intersects? Then there are 4 segments. In the first segment, this dot is below both of these lines. That means both of the species are going to win and will try to reach an equilibrium. This dot is above both these lines, so the species will lose and will try to reach an equilibrium towards center. Same here. This is below blue line and above yellow line, so species 1 will win. And this is above blue line and below yellow line, so species 2 will win. And here, that means that in these kinds of lines exist in nature between 2 species, species 1 or 2 both can win, and depending on the situation. But there can be a 4th situation where you see this K1 and K2 values are inside now. Initially, the K1 and K2 values are outside. Now they're inside. The lines have just crisscrossed. four situations. First situations remains the same. Second situation remains the same. Now the third situation and fourth situation will be such that all of these situations where the species will try to coexist. They will not try to outcompete each other, rather they will try to coexist. So species and 1 and 2 coexists. There are four situations in Lotka-Volterra model, mainly four. There are many other types, but that's enough for this lecture. But there is a problem with this coexistence idea. Later on, uh, uh, Georgi Gauss actually proposed this hypothesis. Two species with identical niche cannot coexist together indefinitely. That means ultimately one species will outcompete each other. So this is the limitation of Lotka-Volterra model, that people found out later on that Lotka-Volterra model can be good only if you consider predator and prey and not consider environment. Whenever you are considering environment, then the model actually is wonky, doesn't really uh, work all the time. So they came up with this idea of competitive exclusion principle that two species cannot coexist indefinitely where they are both limited by the same resource. So scientist Tillman came up with this resource-based model. Same kind of idea like Lotka-Volterra model, but rather than number of species being on the x and y axis, now you have resources. So resource was divided into A and B, and from the perspective of resource, there are different outcomes possible. This is not part of your syllabus, but if you really are interested, you can go and read about it. This is a fascinating part, how Lotka-Volterra model can be further improved. I'll quickly summarize the extreme examples that can be used where Lotka-Volterra has been used. So one example is using the same predator-prey model. Now the predator-prey becomes anything. It can be two inanimate objects, and you can still apply Lotka-Volterra model. And it was used to calculate different things in climate change. Or it can actually be utilized to calculate out different factors in host and parasite interaction, and many other things, enzyme kinetics, any other biological components where there are predator prey kind of interaction, consumption and destruction. Incidentally, that this kind of model has been used in cancer therapies as well. So where the host immune system is the predator, and the tumor cells are the cells which can generate or metastasize as tumors, are considered as the prey. And now when the cancer will occur, when a benign tumor can become a cancerous tumor, all of those calculations are also possible using Lotka-Volterra models. Similarly, Lotka-Volterra models were used to calculate out antibiotic resistance properties in bacteria. And recently, Lotka-Volterra model has been used to analyze COVID-19 and what is the outcome of COVID-19 infections. And this is in the early phases. The exact outputs will take some time to calculate. And with that, I'll go to the conclusion section. So what I really wanted to tell you is that, yes, there is Lotka-Volterra model, but there are so many different aspects of mathematical model that you should explore. There are things like Bayesian network, the different network theories, information theories, systems theories, which I cannot discuss this today. But if you are interested, you can really just take an ecology textbook and you'll find different aspects of it. Is it still? Am I still audible?
Yes, you are.
All right. Okay. So the take-home message from today's talk is that there are two species if there are two species which are competing against each other, the Lotka and Volterra postulated that species 1 will affect the number of species 2, and the distribution they used was Kolmogorov equations to calculate out the coefficient of competition, that is alpha or beta in case of species 1 and 2 respectively. And this is the only model where this both of the species will coexist. So if you remember this, you and if you remember the gist of Lotka-Volterra model. But what I want you to follow up is learn different aspects of mathematical modeling, which you can use for research, but also you can become a data analyst, because Lotka-Volterra model can be used in different aspects of banking sector calculations, population growth, for making predictions about what would be the economic policies of a government. So there are many ways these kind of mathematical models can be utilized. So you just open up that avenue for you, but just explore that possibility. And I thank you for your presence. I'll be happy to answer questions.
So I request the students to ask the questions if they have any. Souvik, so I think it's a nice presentation. So what message do you want to convey to the students?
Don't be afraid of mathematics. Mathematics is beautiful.
Okay, thank you. That's a nice suggestion to the students. So I think besides some minor technical issues, we really enjoyed your lecture. So on behalf of Zoological Association of Bardwan, Dr. Manavesh Majumdar will convey the his sincere vote of thanks.
Uh, I'm audible, Sham? Hello.
Yes, you are.
Yeah. So thanks a lot, Sham. With extreme pleasure, I congratulate and thank Dr. Souvik Bhattacharya for excellent, lucid, informative, yet highly academic lecture, which surely will imbibe the sense of Lotka-Volterra concept deep into the sense of understanding in the mind of the students. I deeply thank the students for their cooperation in patiently hearing the lecture. I also thank the organizing personnel for nicely organizing the seminar. And with this few eulogy, I conclude the session. Thank you.
Thank you
Thank
very
you.
much. With this, we conclude the session. Thanks.
Thanks.